So I want to talk about part E of the project first, okay? It's the trickiest part because I want it to remain abstract. I don't want you calculating things in it. I want you to do algebra, okay? So part E is all about error, and that's a coincidence. It's about error. And we learned how to calculate error before. Grace, I just started. You got chapter 4 materials in front of you, okay? It's also on Blackboard, so you can zoom if it's a little bit too small to read, okay? And I did take my health self-assessment today. I am not sick. No one in my family, no one in my apartment is sick. So I think you should feel safe about taking the papers from me. If I am sick, I'm not coming in. I do it every day. I don't know if you do it. Self-assessment at the top of the webpage. Are you having any symptoms, et cetera, et cetera? There's a new wave coming. It's in Europe right now. Hopefully, I don't know. What are we going to do? We're going to live with it for the rest of our lives, I'm sure. Okay, part E is all about error. We learned how to calculate percent error in bio class or whatever, chem class. We're going to take the absolute value of the actual answer minus the experimental answer, right? All divided by the actual. We're using the absolute value because we want a positive number, right? And this will give us our percent error. Do you remember doing this ever? Yeah. So if you were doing some bio experiment on boiling water, right? And I think we know the temperature where water boils or whatever. And, so you would get how off your, whatever is going on with your experiment. Who cares? So we're going to get an initial error from our problem. And we're going to get a next error. Okay? Related to X next, right? Related to the next guess. Yes, you with me? And you're going to show, once you get those two pieces, you're going to show that the initial error squared is the next error. So doing some algebra, obviously, you're going to have to do some factoring or, it looks like maybe foiling there, right? So you're going to do something to show that the two, that gives you, that you'll prove that, okay? So there's no numbers involved in it. What's the actual problem having you calculate is the reciprocal of pi, right? So I forget what it is. It's either b equals 1 over pi or, right? I think it's not that. I think it's 1 over b. So meaning now I know what I should actually get. And of course I could do 1 divided by pi on my calculator, right? We did that the other day. Did we? It's like 0.3 something, right? 1 divided by pi, 0.318309886183791, almost. So I know what I should get. I should get 1 over b, right? But what is my guess for the answer is my initial guess. So my initial error is 1 over b minus x all over 1 over b, right? And of course, make it positive. Or who cares about the positive negative if you keep them both in the same order, right? So the initial error is coming from the initial guess, right? Does that make sense? Right? if you say 1 over pi is 0.3, right, that's your initial guess. And so we're going to calculate the percent error there. Okay? 0.3 is pretty damn close, isn't it? 0.3 is pretty damn close, right? I have the calculation right here on my phone, so let me just, so kind of just a side idea here, it's 0.3183 minus 0.3 over 0.3183, right? So minus 0.3 divided by 0.3183. So I get 0.057. I get 6% error from my initial guess. Think about 6% error. What do I get if I square that error? What happens to the error? Gets smaller. So I get 0.3. I get 0.036, right? I get almost about 4% error. So every time I square a number less than 1, it gets smaller, right? As long as it's between 0 and 1, it gets smaller. All right, what's my next error going to look like? Did I hit record? Yes, I did. I did. Yes. What's my next error look like? Well, it looks like the other error, but instead of the initial x, what's going to be there? X next, yes. So 1 over b minus x next over 1 over b, right? Remember, you're going to make these things look pretty, right? Do the algebra to make it look pretty, right? Meaning completely factored, numerator, denominator, no fractions within fractions, right? So, but what does this become? Because we know our x next formula now, right? What does this become? It's x minus f of x over f prime of x. Yes, you with me there? So it's with these two pieces, and if you just came in, I'm recording, okay? This is the first thing I'm doing today. I'm talking about part E for the project. You need these two formula to be able to solve part E in the project. Diane, I have your test here, and do you mind grabbing this for me, the project? And on the desk where everybody's sitting, I have chapter 4 materials. Okay, review materials. You can work on the project up to a group of 3, okay? You can work on it alone, you can work on it with one person, you can work on it with 3 people, okay? I think if you do it with 3 people, max 2 hours. You can do one, you could do it alone, you could do it as a group of 2, or you could do it as a group of 3, right? So those 2 pieces are what you need. The mistake I usually get there is that you start giving me calculations. I don't want calculations. I want algebra. All I want to show is this, right? With these 2 formula, with your function in place, right? You're going to show me that my error gets squared, which is important because if the error is very small, when I square it, it gets smaller. And eventually goes to what? 0. If I keep squaring a number between 0 and 1, it's going to eventually go to 0. And that's when we know we have our answer in Newton's method, right? It was really quick, right? Remember, on Tuesday, I think I had one that was 3 iterations, and then the rest of it was the same, right? And then I had another one I think was only 2 iterations, right? Once I did the process twice, I was done. Okay, so that's the piece on part E. I think that's the trickiest part of the project. The rest, trust your gut on it. It really reads so nerdy. Okay? So when you're reading it, you got to try and put my voice into it of what I was saying. Oh, I'm just finding the x-intercept of the tangent line. Oh, maybe I can write the formula nicer, right? With less subscripts, right? That's part A and B, okay? Part C, I did it. All you got to do is repeat, right? Part D is finding this reciprocal of pi, so you're just going to create a new function like I created the function from part C. Part E is almost done for you here. And part F is the discovery of when it fails, right? There's 3 questions. There's 3 instances when Newton's method fails. When I get my tangent lines just running away, when I get an oscillator, so tangent lines just going back and forth between a positive and a negative, okay? And then obviously from the formula for x next, when I get a derivative of 0, I'm in trouble, right? You can see here I'm going to divide by the derivative. If I get a derivative of 0, I'm in trouble. So if I got a bunch of functions with tops of hills or bottoms of valleys, like a sine curve, right? Can you see it? Bunch of tangent lines that are 0. As soon as I hit one of those accidentally, Newton's method fails. So little subtleties like that. Hey. That's chapter 4 review material, Daniel, okay? It's also on Blackboard. Nice. Let's do a problem from last class, right? So you've got your chapter 4 review material there, bottom right corner of that first page. I've got a function of negative x times square root of 3 minus x. Yes, you with me? So this is 4.2. This is going to be your first quiz. So I want to find the absolute min and max, right? Find the abs, min, and max. On, what does it say, negative 2 to 3? For f of x equal to negative x times square root of 3 minus x. Now, I'm saying you should probably be able to graph this on your own, right? You know something about the square root function, right? Yes? You know what this regular square root function looks like. It opens to the right. Does this one open right or left? Yeah, this one definitely. So if I was doing this on my own, I would just say, all right, I know what the square root looks like, right? That's this guy. If I do 3 minus x, I know the 0 is going to be 3, right? So I know it's got to hit a height of 0 at 3. And what's telling me it's moving this opposite way is, right? Think about if I put a 4 in there, I get a negative number. I can't, right? You got to think about the domain, right? And now what's going to happen to this guy as I multiply by a negative x? Yeah, so what do you think is going to happen if I multiply it by just a negative? It takes all the positives and makes them negatives, so I flip this way, right? Right? Just say yes for me. Yeah, okay. And then if I now multiply it by a factor of x, think about what happens to when that x is 0, what happens to my curve? It's got to hit 0, right? So you can kind of see it getting bent like that, right? So from some negative 2 to 3, right? But of course, what are you going to do on your test? And what are you going to do when you do your homework? And what are you going to do when you do your quiz on this? You're going to graph it, right? You don't have to be able to do it from memory. You should be very good at that in Calc 2 and forward. Should be very good at graphing things after Calc 1. So y equals negative x times the square root of 3 minus x. And we want to restrict our domain from what? Negative 2 and positive 3, right? Nice. So we can already see the answers, right? And this is what I love about the rest of this whole class is everything you will know if you have it right or not. Every problem we've done, you can know if you're right or not during the test. If you're practicing that, you got to practice that. So I can already see the max is going to come at my endpoint. Yes, the highest point of the curve is at the endpoint. And the lowest point of the curve is going to come at the critical value. Do you see the horizontal tangent there? Do you see a horizontal tangent at that low point? Yeah. So you know you're going to get a derivative equal to 0 there. Nice. Good. So back here, what was our process? Find the value of the function at, well, graph it, right? I gave you a checklist, right? So graph it. Find the value at the endpoint. So f of negative 2 is 3 minus a negative 2. And you're not copying me here. You're doing the work yourself, please. So 2 rad 5. Right? You can get a decimal so you have a better idea of it. Rad 5 is about 2.24. So $2.24 doubled is $4.48. So 4.5, it should look like on my graph. Definitely looks like 4.5, right? Do you see it? So what did I say? Negative 2, comma, 2 rad 5, right? There it is. Beautiful. I love it. I love knowing I'm right, especially when my girlfriend's wrong. Doesn't happen often. F of 3 is negative 3 times square root of 3 minus 3. Okay, that's just 0. So I know 2 rad 5 is a possible max. In fact, I know it is the max, right? But it's bigger than 0. It's bigger than the other option, so I know for sure 0 could be the min. But again, I know the graph. I already know the answer, right? I already know the answer. All right, what do we have to do next? We have to find the derivative, right? Yep, so you're racing me. You're not copying me. You're doing the derivative on your own, damn it. I could factor out a 3, but it doesn't change much for me. Anybody get there? Nice. Everybody else, get on the horse. Let's go. Nope. I will in a second. I want you to try it. I want you to try it. I want you to get the derivative. Product rule. Pretty friggin' simple. I will go back up, Claire. I didn't eat breakfast today, so I'm in a bad mood. Here it is. All right, we graphed it, right? We found the value at the endpoints. We found the derivative, yes? Checklist is pretty simple, right? Should you have this on your formula sheet for the test? Yes. If you want to get that one problem right. All right, now what's next on my checklist? Find the critical values. There's a subtlety in that I want to find the critical values in the open interval, but I might as well just find them all because it's easy, right? And then cancel the ones I don't want, right? So I know I get f prime of x equals 0 when when the numerator is 0, right? That's when x is 2. Yes? And notice that 2 belongs to negative 2 to 3, right? You agree with that? It belongs to the open interval. Claire, you okay? Yeah? I get a critical value downstairs as well, right? F prime of x does not exist implies that 2 square roots of 3 minus x equals 0, which means x equals 3. But that does not belong to my open interval, right? It belongs to the closed interval, but I don't care about checking the height of the endpoints again. I already know the height at 3 is 0. I don't care about doing it again. So I have only one critical value, right? So I need to find f of 2. Oh, that's pretty easy. Negative 2 times square root of 3 minus 2 is negative 2. Sweet. And that's the low. That's the min. At this point, I want to go back to my graph. Remember, I'm going to write a conclusion, right? But I want to go back to my graph and make sure I got it right? And I'll see it instantly. I'll see that low point is at a height of negative 2 instantly. I don't even have to graph it. Look at it, the height of negative 2, right? So I had 3 comma 0 was my other endpoint, and I had 2 comma negative 2, right? And there it is. I know I'm right. Feels good. Feels good to be right. So why didn't I use the x equals 3? Yeah, so remember our critical values are when the numerator is 0 or the denominator is 0. But this denominator of 0 that I got, right, is the endpoint of my interval. And remember, I'm trying to find these numbers to plug into the function. I've already plugged 3 into the function. I don't need to bother with it again. It's a subtle point. I mean, you could say it's still a critical value and plug it in, but you're going to get 0 again. Notice I'm not plugging the 2 into the derivative, right? I'm plugging the value that I found back into the function, and we're going to do that quite a bit in this chapter. We're going to find critical values of the derivative and plug them back into the function. We're going to find critical values of the second derivative and then plug them back into the function. We're asking, what does the derivative tell us about the graph, the original function? What does the second derivative tell us about the original function? In Calc 2, we'll do a fourth derivative and a sixth derivative. Okay? It tells us something about the function. Easy, right? Yes? Just lie to me. Easy, right? Okay, good. And then I write my conclusion, which I don't feel like doing because I'm lazy. But I found my absolute min at this height. I found my absolute max at this height. Nice. We're ready for new stuff. So there's a bunch there. I do like the ones for homework. I think I decided this already. Make sure you do the trig ones, because most likely I will put a trig one on your first quiz, even though it's not in the homework. Why am I doing that? Because you're evil, Robert. Yes, I am a little bit evil, but also because if you don't know your trig, you're not going to make it in Calc 2. I need you to know how to do the trig. 4.2. So 4.2 homework. I would like you to do all of 41 to 54. But for your homework, I'd probably like 47, 49, 51. I'm thinking that's going to be your first 3 homework assignments. But make sure you do the trig one too. Why don't we do 53? So 2 cos x plus sine 2x on 0 to pi over 2. This is how bad my brain is right now. I think it's just because I'm getting old or something. I don't know what it is. But I got to take a photo of it or I'm going to forget it when I... So this is 4.2, number 53. F of x equals 2 cos of x plus sine 2x on 0 to pi over 2. I mean, pretty easy to graph, right? We should do that because that's how we're going to check ourselves. Where did I put my graph? Did I close it? Oh, no, there it is. There it is. Pretty simple, right? We get the min value from the right endpoint, and we get the max from a critical value of the derivative, right? Where the derivative is equal to 0. Yes, do you see it? You see it? You can see the top of a hill. My skis are horizontal there. That means a slope of 0. That means the derivative is 0. Right? I already know I'm not going to get a denominator out of this derivative, right? Don't I? It's pretty obvious I'm not going to get a denominator out of this, right? Yeah. Good. Let's find f of 0. That's 2 times cos of 0 plus sine of 2 times 0. Cos of 0 is 1. Sine of 0 is 0. So I get 2. Looking at my graph, I definitely see 0, 2 there, right? I don't have to plot it. On my calculator, I don't have to plot it, right? I see it. I already know the answer to f of pi over 2 should be 0 because I can see the graph, so it's nice, right? But 2 times cos of pi over 2 plus sine of 2 times pi over 2. Oh, cos of pi over 2 is 0, and sine of pi is 0. And yes, you should know your trig that well. If you don't, you can use your calculator, but you're wasting time. I still want to know how some of you skip trig. I want to know. I already know how some of you skip trig. Derivative. You're not copying me, damn it. You are not copying me. You are doing the derivative yourself. Anybody agree? I don't get the absences. I tell you that. I remember skipping a class every now and then, and I'd come back in the class and they'd talk about M. The letter M. What the hell is that? Right? In a math class, you skip a class, then all of a sudden next class they're talking about crazy stuff. Stop missing classes. See, DeLeon is out. Kevin is here. Marinata is out. Who else is out? Marco. Damn it. Anybody else get the derivative? Only 2? Diego? Nice. Yvonne, you got it? What do you mean? There is only one part. So the derivative of 2 cos x is negative 2 sine x, right? The 2 comes for the ride, right? Then, oh, I made a mistake, didn't I? I made a mistake, didn't I? I'm wrong. Didn't I make a mistake? Derivative of sine x is cos, sine 2x is cos 2x. Oh my God. So cos 2x, right? But the derivative of the inside is 2, so I was wrong. Sorry about that. Did you get that? Did you get that one? Good, because the other one was wrong. The question is, did he do it on purpose, or did he actually make the same mistake that you will make, right? So, what do I have to do? Once I found my derivative, I have to set this equal to 0, right? So find the critical values, right? So I know that negative 2 sine x plus 2 cos 2x should equal 0. I can cancel the 2's there, right? So I can divide everything by negative 2. And I get sine x minus cos 2x equals 0. I know from how much work I did in my trig class and my pre-cal class, I have an identity for cos of 2x. And I've got my identities on my formula sheet, right? So I can look and see which one makes the most sense. There's 3 of them for cos 2x. Cos squared x minus sine squared x, but then I still have a cos squared in the answer. And the other one is 1 minus 2 sine x. That's the one I want. So sine x minus 1 minus 2 sine x equals 0. Sorry, it's 2 sine squared x, right? Yeah. Anybody have their formula sheet with them? Is that correct? Yeah, I have an answer. I think the identities for cos 2 theta, and that's what I'm asking, is cos squared theta minus sine squared theta, or 2 cos squared theta minus 1, or 1 minus 2 sine squared theta. That's what I'm asking on your identities. Do you have that third one? One minus sine? This is it. This is it. Yeah. So what do I get when I simplify this? Sine x minus 1 plus 2 sine squared x. And I notice, and I did so many of these in pre-cal and trig, that I notice it's a quadratic. Because I took trig. I took pre-cal. I really am grumpy when I don't eat. So it's quadratic, right? So I get that sine of x equals x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. I get minus 1 plus or minus square root of 9 all over 4. I get minus 1 plus or minus 3 all over 4. I get, so if I take both negatives, I get sine x equals negative 1. Or if I take the negative and positive 3, I get sine x equals 1/2. I know sine x equals negative 1 at 3 pi over 2. I know sine x equals 1/2 at x equals pi over 6 or 5 pi over 6. But the only one that's in my interval is pi over 6. Everything else is bigger than pi over 2. 3 pi over 2 is obviously bigger than pi over 2, right? And remember, I'm only in quadrant 1, right? So pi over 2 is only dealing with that part of the sine function. So my only critical value is pi over 6. Do I have any agreement? Brian, Diego, Ryan, Grace, damn it. How many problems do we have like this? Yep. Yep. Yeah. Yeah. Yeah, so starting at line 1, right? Oh, you want these guys? Yeah. Oh, gotcha. Yeah, if you have the textbook, right? It's the very first page of the textbook, right? The very first page has got front and back has got all of this stuff that you should have memorized from trig. Where are my double angle formulas? They're somewhere. Here they are. All right, so we got our critical value, correct? We got to find that. So x equals pi over 6 is the critical value. And f of pi over 6 is going to be the height, right? So 2 times cos of pi over 6 plus sine of 2 times pi over 6. Well, that's 2 times rad 3 over 2 plus sine of pi over 3. Oh, that's rad 3 over 2. 2 times rad 3 over 2 plus rad 3 over 2 is 3 rad 3 over 2. And that's my height. That's my max height. Yes, Grace. Yes. Tell me, where is it? Enough? You want photos of the whole thing? Yeah, let's go 3 photos. Good. Yes. Might be 4 photos. Oh no, that was it. Yep. I want to double check it. I want to make a conclusion, right? So double check. I can go to my Desmos and plot that point. I got pi over 6 as my critical. And then I got 3 rad 3 over 2. 3 square roots of 3 divided by 2. There it is. Ha! We are the champ. Right? We got it right. Yes. We're the best. The best of the best. All right, here we go. Let's take a little break. Let's come back at 10:05 and then we'll do the first derivative test. Let me pause my recording. I teach in 2 pieces. So we're talking about the first derivative test here. Do you remember in pre-cal when we did the sine tables? My 4 students in pre-cal, you remember the sine tables? How much hell they were? I put you through that hell because I'm going to make it a lot easier now, but because we need to do a sine table when we do a first derivative test, but we're going to make it easier. But I needed you to be tortured first, okay? Because I wanted you to know how to set them up and what was really going on behind the scenes of a sine table. Because when we do them in Calc 1, we do them much simpler, okay? So the first derivative test is very, very simple. It's going to tell us something about the function once we find the first derivative, okay? And the basic idea behind the first derivative test is if f prime of x is greater than 0 on some interval I, then f is increasing on that interval. So if you think about it, right? Let's take square root function. If you think about the slopes at any point, what kind of number am I talking about all those slopes? Is that a positive slope or a negative slope? Positive slope, right? Right? Positive slope. So I know in this case, so here's something that's always increasing. look at my derivative, right? If y equals square root of x, what's y prime? You remember? You better, damn it. 1 over 2 square roots of x. Remember, I'm only putting positives in there, right? So that's always positive. The derivative's always positive. So, but again, look, can I graph the function? Can I tell when it's increasing? Hell yeah, so I'm going to be able to cheat this the whole way. I'm going to know I have this thing right. It's just the process that is horrible, okay? The process is horrible. So, what else do I know from first derivative test? If f prime of x is less than 0, then f is decreasing. So what we want to be able to find are all the intervals where the function is increasing or decreasing, right? And that's our first derivative test. Okay? I mean, right? We're making money, right? We want our derivatives to be positive. Sound familiar at all? We want our returns to be positive, right? So we're looking for when are we making money, and we're doing that by looking at how things are changing, right? We're looking at better blood pressure, right? We're trying to get the blood pressure at the right rate, right, to heal a patient kind of thing. So we're looking at how things are changing, right? We're always going to be looking at derivatives. How things are changing is going to tell us something about the original, right? So that's basically what's going on here. All right, step by step. Here we go. Nice and easy, right? It's easy when you have step by step. Not really, but right. So we want to write for the first derivative test. Now the book tends to give you a function and says do the first derivative test and do the second derivative test. So I'm just teaching first derivative test today. Tuesday I will teach second derivative test. So if you start doing problems in section 4.3, it'll ask you for everything. Don't do everything. Just do the first derivative test for now. Okay? Once you can do the first derivative test, the second derivative test is just as easy, but just as painful. Okay? So first thing, graph the function. Right? We're looking for when is the function increasing or decreasing, right? Step 2, find f prime. Find the derivative. We are doing a first derivative test, right? Find the critical values. Now the critical values of the first derivative could be partitions, or they could be critical values. So for example, like 1 over x, what's it doing? Or better yet, 1 over x squared, right? What's it doing on the left half? Increasing or decreasing? From the left half, what's it doing? Increasing or decreasing? Increasing, and the right half's decreasing, right? And if I think of y equals 1 over x squared, y prime is going to be negative 2 over x cubed, right? And obviously there's a critical value of 0 there, but that point doesn't exist on my original graph, so we tend to call those partitions. I don't care about the language. I still want to call it a critical value. But do you see what I mean by a partition? It's cutting it into the two pieces of the graph. So it's right. So a critical value could just be a partition, or it could actually be a point on the graph. And the book tries to say that elegantly, but who cares? Okay? So find the critical values. create a sign table. Let me hear the moans. Do you remember sign tables from pre-cal? Any of you that weren't in my pre-cal class? Do you remember doing the sign tables where you had to see where the function was above ground or below ground or, oh my God. Create a sign table using a number line and the critical values. So for example, I only have one critical value of 0, right, for my particular curve here, right? So I got my y prime, I got my critical value of 0. Yes, you with me over on the right side? I got my critical value of 0. Can I plug it into the function? No, so I'm trying to keep it as an open, right? I'm trying to keep it as an open hole on the number line. Create test values for the first derivative. So I see that -1 and n plus 1 will work. That's fine with me. So wherever they're in between my criticals, I want to put test values. You with me? I keep zooming and I keep forgetting I'm not allowed to zoom. That's okay, right?
What is the second word on number 5?
Create test values. Yeah. So these test values, remember, it's called the first derivative test. I'm going to put these values into the first derivative. And what am I choosing? Anything I want in between my criticals. Left of, right of, and in between my criticals. You remember doing this, my pre-cal students? Left of, right of, and in between. Yes. Horrible, right? You wanted to kill me then too, I know. Left of, right of, and in between all the criticals. Some of those criticals could simply be partitions. Some will actually be of value to us, okay? Step 6. Find the sign of f prime of c on each interval. Find and label the sign of f prime of c on each interval. Uh-oh. Battery. Remember when I told you that this is a horrible process? Do you remember me saying that? Lots of writing. You remember me saying that? Yeah, it's horrible. Believe me. Find and label the sign of f prime c on each interval. 7. State the intervals where f prime of x is positive and f is increasing. Where f prime of x is negative and f is decreasing. So we're getting, when our derivative is positive, we want to state that interval and say that f is increasing on that interval. Same thing when f prime is negative, state that interval, and where the function is decreasing. 8, where f prime of x changes signs so from positive to negative or negative to positive, there is a possible min or max. And they're local min or maxes. They might not be the absolute min or max. They could be just the top of a hill, right? Or the bottom of a valley, but then there could be another one that's even lower or another one that's even higher. Who cares? So we're calling them local min or max. If f of c exists and f prime changes from negative to positive, think about it, negative to positive, it's a local min. C comma f of c is a local min. If, yes?
So on number 8,
Yeah.
it says, when it changes, there's a possible min or max. When wouldn't there be a min or max?
When it's a partition. So at 0, so notice, so I didn't do this, right? But when I put a negative 1 into that, yes, I get negatives, right? I get a double negative, so I get positives, right? So there's my sign. When I put a positive 1, everything stays negative. So you can see my derivative is changing from positive to negative. But f of 0 doesn't exist. So it's not a local min or max.
Yeah, I saw what you were saying. It's just that when you, when you're finding a min or max in the past, we've always had the intervals. So then when there's an interval, there's usually, I don't know.
Yeah, you'll see. I'll do a couple of examples. You'll see, like this is the easiest case to show you that there's no min or max between those two, even though the derivative's changing from positive to negative, right? So you could imagine the top of a hill, but there is no top of the hill, right? Where f prime changes signs, there's a possible min or max. I need the point to exist, though. Right? So that's the issue. So if f of c exists and f changes from negative to positive, it's a local min. If f of c exists and f prime changes from positive to negative, then c comma f of c is a local max, right? Positive to negative. It's the top of a hill. So step 8 still, state the local mins and maxes. State and justify the local min and max, if any. Done. Ha! Only 8 steps. Only 8 steps. Yes, picture.
No, this is number 8.
Okay. I didn't get all of 8. Do you want the first part of it? I don't.
Actually, that would be better.
Yeah, I don't want to zoom because so your pictures are in reverse order. That's all.
Yeah.
Yep. I don't want to zoom because I lose a little clarity when I zoom. All right. So is any of this difficult? No. Do you know how to take a derivative? Yes. Do you know how to find critical values? Yes. Do you know how to do sine tables? You better. It's just the writing. It's just a lot of writing, right? It just sucks. But we can handle it. Let's do an interesting one. Where is my book? Nice. Let's go to 4.3. Polynomials are boring. Second derivative test concavity. So concave down like a turtle's back. Concave up like a bowl. Okay? So second derivative will test for concavity. Oh, that looks like a nasty one. That looks nasty too. So you'll see here, like in problems 21 to 32, it'll say find the intervals of increasing or decreasing. And find the local min and maxes. That's first derivative test. Then find the intervals of concavity and the inflection points. That's second derivative test. So right now, just restrict yourself to first derivative test. Okay. Cool. Let's do 33. Oh, I like 37 too. Let's do 33 and 37. Where's my phone? Here it is. And then we'll go home. How's that sound? Or whatever. Or what? We'll go to our next class? Anybody going to another class? Oh, God. Sorry. Me too. I'm going to another class too. Anybody going out to breakfast after this? Oh, I'm jealous. So jealous. 33 and 37. Let's do the first derivative test, okay? You with me? So, f of x, so this is a 4.3 number 33, but only first derivative test, right? Not doing everything they're asking me for. So f of x is x squared over x squared minus 1. You can already see a couple of things from pre-cal, right? That we have vertical asymptotes at plus and minus 1, and a horizontal asymptote where? At 1, good. You can also see I have 0, 0 as a point, right? And so I pretty much can guess that the graph looks like this. Of course, what can you do? You can graph it on your calculator, right? You can definitely graph this on your calculator. In pre-cal, we taught you how to graph all these types of functions. So, but just to be safe, I want to make sure I graph it when I'm taking my test, right? So f of x equals x squared divided by x squared minus 1, right? So there it is. Now notice what's happening on the leftmost part of my curve. I'm increasing, right? Yeah. So look, I already know the answer, right? On the middle part of my curve, left-hand side of it, I'm still increasing. And notice I have a partition there. The graph's not connected. Then my function starts to go back to decreasing, and notice I have a top of a hill there, so I'm going to have a local max, right? And then on that right-hand part of my curve again, I'm decreasing. So I'm going to have one interval of increasing, one interval of decreasing. with unions, and all of that. And I am going to have a local max. So I can see everything from the graph, right? But you have to know this is happening in the year 1800, okay? This stuff is being discovered in right after the plague, okay? And so it's not that they didn't have calculators. They did. They didn't have batteries. No, I'm kidding. So we're doing all of this to be able to talk about functions and what they're doing without any kind of technology. We are given a little bit of an advantage of that we can get all the answers from the technology, but we would still want to understand the classic of how it's happening, the calculus, okay? All right, here we go. Step 1, done. Yes? What's going on? It's freaking. Oh no, don't do it to me. Ooh, thank God. Okay, step 1, done. Step 2, remind me. Derivative. On your mark, set, go. Do not copy me, damn it. Oh, good. Now you can't copy me. I don't know what's going on with my cable here. Let me get it. Nice. Anybody need to see it? It's cool. We're not doing anything different than we did before spring break. We're just taking derivatives. It's easy. It's fun. You know when you get them right now. Next step, criticals. Step 3, criticals. Yeah. So it's usually I'm able to see it pretty quickly. If I have to do some algebra, I can. But obviously my criticals are plus and minus 1 and 0, right? You agree? Upstairs is 0, downstairs is plus and minus 1. I know downstairs are my partitions, and upstairs is an actual local max, right? Step 4 is my number line. Is that correct? Yep. So number line. At -1, I got a hole. At 0, I don't have a hole. And at 1, I have a hole. Right? At -1, at 0, and at 1. It's kind of nice. I like to actually put in the holes as parentheses and the non-holes as square brackets. because the parenthesis, I can't get to it, right? The square brackets, I can get to it. So when I'm writing my intervals, it's nice to think about that a little bit. I need to put in, are we okay here? We're okay? Test values is next, is that right? On my list, 5 test values. So anything left of -1, look at it. Look at the graph. Anything I put left of -1 is going to have a positive derivative there, right? Because the slopes are slanting up. So it doesn't matter what number I pick, right? If I pick -2, do you see I get a positive slope at -2? What if I pick -4? Wouldn't I still get a positive slope? So that the critical values are telling me the separations of where the function is changing. So I like just -2 here, +2 over here, and it looks like what, -1/2 and +1/2. So you see I'm going to have to test 4 places in my derivative. I've got 4 test values. I need to test 4 times. The test is easy. I can cheat it, okay? The test is easy, right? F prime of -2 is -2 times, is it -x? No, -2x, right? So the downstairs is not going to change no matter what number I put in because it's squared. So you can see I'm going to get a positive here. But I can cheat the positive from my graph. I already see that the graph is positive here and here, and the graph is negative here and here. I don't really need to plug in the numbers. I can cheat it from the graph. Sometimes the graph might be hard to tell. Like in the second example we do, it might be really hard to tell. So, but I certainly can plug it in. It's not difficult to plug it in, right? Step 6, help me. The signs, right? Step 5 was create the test values. Step 6 was put the test values in, right? 7 is my intervals, correct? Am I right? I just don't remember. So f prime of x is positive on the interval I, which is from -infinity to -1, union -1 to 0. Notice I'm using those bracket pieces there, or the parenthesis pieces. So f is increasing on I. I got to do a conclusion for increasing intervals, decreasing intervals, and any of the local min or max. There could be more than one local min or max, so then I got to do a conclusion on each of them. F prime of x is negative on j from 0 to 1, union 1 to infinity. So f is decreasing on j. A lot of writing. Sucks. I already know where my derivative changes signs, right? From my table, isn't this sign table so much easier? Grace, Diego? It's so much easier than how I tortured you in pre-cal, right? But you really know what's going on here now. F prime of x changes signs at x equals 0, and f of 0, which is 0 squared over 0 squared minus 1 equals 0, exists. It's a real number. That's what I need it to do, right? Since f prime of x changes from positive to negative at x equals 0, 0 comma 0 is a local max. Done. Ah. Told you, horrible. Boring is all. Boring, boring, boring. I'm probably not supposed to say that stuff to you as a teacher, but that's the way I felt when I learned this stuff too. Like, oh my God, what a waste of time. Thank God in Calc 2 we don't do these things. We do a couple of other things that are hideous, but at least we don't do these anymore. All right, let me stop my recording because it's enough. The process is the same, but let's do one more problem and then quit. Okay? Sound good?